Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Chemical Reaction Engineering Part 4. In this section, we will be discussing catalytic reactors. In this course, you will learn an introduction to catalytic reaction, types of catalytic reactions, catalyst activity, catalyst deactivation, catalyst stability. Catalytic reactors. Catalytic reactions involves use of catalyst to carry out a reaction process. A catalyst is a substance which provides an alternative route of reaction where the activation energy is lower without actually taking part in the reaction. Catalysts do not affect chemical equilibrium associated with the reaction. They merely change the rate of reactions. Generally, catalytic reactions are classified based on number of phases as homogeneous catalysis, in which catalyst and reactants are in the same phase; heterogeneous catalysis, in which you have a solid catalyst and the reactant is a gas or and liquid. Homogeneous catalyst typically forms a complex with one of the reactants which eventually transforms into the product after interacting with other reactants. This figure illustrates a homogeneous reactor. The catalyst solution is initially added to the reactor. The reaction rate is controlled by the addition of the reactants and the contents are kept under constant agitation. It is a CSTR. The reactor is jacketed for heating if needed. The process is essentially similar to the homogeneous reactions in the absence of catalyst and is often controlled by mixing of the reactants and catalyst species at molecular level. In contrast to this, in heterogeneous catalysts, several additional steps are involved along with reaction occurring on the catalyst surface. Shown in this figure is a heterogeneous fixed bed reactor of length L. The feed enters the top at a concentration of Ca0 and products leaves the bottom with the reactant concentration of Ca. Since the reaction shown is reversible, the conversion is limited by equilibrium. This is an illustration of a cutout of the reactor catalyst bed. The gas stream in light blue color flows through the bed of catalyst denoted by circle in dark blue stripes. This figure illustrates the 5-step process in the catalytic reaction. In step 1, the reacting species diffuse from the bulk fluid to the catalyst surface. The step 2, the reactant gets deadsorbed on the active sites on the surface of the catalyst. The step 3, surface reaction takes place. In step 4, reaction products gets desorbed from the active site. In step 5, the products diffuse from the catalyst surface to the bulk fluid. Heat transfer, interface mass transfer, and chemical reactions are important characteristics of the catalytic processes. They play a crucial role in determining the performance of multi-phase catalytic reactors. Worth mentioning here is the polyolefin production process, which is a well-mixed heterogeneous catalytic polymerization process. These heterogeneous polymerization processes are impacted by gas-solid flow properties as well as hydrodynamics. Rate of reaction is influenced by the temperature and composition of the components in the reactor, as we discussed in the earlier courses. The reaction rate with respect to the reactant A is given by the expression minus RA equal to K into concentration of ACA to the power m, where m is the order of the reaction. The expression for the reactant constant K is K naught into e to the power minus E by RT, where K naught is Arrhenius coefficient and E is the activation energy. Hence, the rate of reaction is a function of the energy level, which is the temperature, and the concentration of the materials. From the rate equation, you can notice the term activation energy E. As the activation energy increases, the reaction rate decreases. Certain reactions need large activation energy or very high temperature to begin the reaction or proceed at an appreciable rate. The catalyst reduces the activation energy required for such reactions and break the barrier that exists to initiate the reaction at lower energy level or temperature. This chart is an illustration of how catalyst lowers the energy level in a chemical process. This figure is a plot of energy of reactants versus progress of reaction. You can observe the activation energy required for the reaction without catalyst is higher. With catalyst, the activation energy gets lower. The red circle indicates energy saved in the catalytic process, shown in the grey hatched area. With catalyst, energy barrier gets lower and hence high reaction rates are achieved. Catalyst properties. Physical properties of the catalyst have a significant impact in its performance. The The most important catalyst properties are: 1. Surface area expressed as meter squared per gram of catalyst. The second one is the pore structure. These two properties determine how easily the reactants and products can travel to and from the active sites. Usually, the catalyst particles are in the form of pellets. The catalyst activity is an important parameter in determining the reaction rates or conversion in catalytic reactions. The activity is the ability of the catalyst to increase the rate of reaction. Which particle size is better for the reaction? Bigger or smaller? But smaller particle size means higher pressure drop in the catalyst bed. Hence, particle size is a compromise between higher activity and catalyst bed pressure drop. Usually, 2 to 3 mm pellets are used. This graph illustrates the relative activity versus particle diameter in an ammonia synthesis reactor. Relative activity is 100% when the particle diameter is less than 1 mm. As the particle size increases, the activity decreases, reaching the value of close to 10 at 13 mm dia. The catalyst activity is much higher for fresh catalyst than the catalyst under use. In reality, several factors influence the activity of the catalyst to reduce over the period of time. To get the required conversion, the initial activity of the catalyst should remain unaffected. That means the activity should be as close to the activity of the fresh catalyst at any point of time. That is a challenge in many catalytic processes. As explained before, catalytic reaction rate is influenced by the diffusion of particles into internal surfaces of the pores. Hence, usually the rate equation is modified by including an effectiveness factor. The rate expression RA given here includes the effectiveness factor. Effectiveness is a measure of utilization of the internal surface of the catalyst. For a given catalyst, the effectiveness factor depends on the particle diameter. Catalyst deactivation. Catalyst begins to lose its activity as the reaction proceeds due to various reasons. As the activity starts reducing, the reaction rate decreases. So in a given reactor catalyst volume, the conversion also decreases. In terms of rate constant, we can write now K observed is equal to K initial value multiplied by Fa, where Fa is a factor for relative activity due to deactivation. The value of Fa is 1 for a fresh catalyst. The value of Fa depends on the type of reaction and what causes the deactivation. The nature of reactions play a significant role in the deactivation. Deactivation is caused by poisoning, sintering or thermal degradation, fouling, mechanical damage. Poisoning. Poisoning is caused by chemisorption on active sites, impurities in the feed or the poisons. Poisoning blocks the sites, may be reversible or irreversible. Here you can find some examples of poisons. Gaseous poisons include hydrogen sulfide. Metal poisons include copper and iron. Shown in this figure are the poisons and the catalysts susceptible to attack by these poisons. H2S is strongly chemically adsorbed by nickel and gets poisoned. Copper becomes active on the surface of nickel and attacks it. Likewise, iron acts on the copper catalyst and produces polymers. Water and chlorine are some of the sintering accelerators on the catalyst. Fouling. Physical blockade of surface by carbon or coke or dust, also called self-poisoning, caused by secondary reactions of reactants and products to form coke. Usually, the activity can be regained by regeneration by changing process conditions, that is by means of heating. This figure illustrates how fouling by carbonaceous material formed largely by coking blocks the pores and affect the mass transfer and kinetics. The pore diffusion resistance increases due to fouling, and conversion decreases as a result. Sintering. Sintering is caused by thermal degradation. A bigger particle forming smaller particles due to degradation leads to loss of surface area, usually a gradual process, usually irreversible. Mechanical damage. Mechanical damage occurs during transportation and handling. It includes loading in barrels and unloading, filling in reactor bed, due to which the damage can occur by crushing, and attritions. Mechanical damage can also occur during startup and shutdown of the plant. The damage occurs by thermal shock due to temperature swing. It can also be due to chemical transformation such as reduction. This graph illustrates how the reaction rate decreases with process time due to deactivation of the catalyst. Activity drop causes the reaction rate to decrease. The shape of the curve is different for different deactivating causes. Loss of surface area or loss of active sites or loss of activity due to blocking of pores due to coking and fouling. Catalyst stability. Deactivation causes the catalyst to lower its stability. Stable activity is of paramount importance in achieving satisfactory catalyst performance on continuous basis. The best catalyst should be highly stable and kinetically favorable. Some catalysts work extremely fast but loses its activity to deliver performance after few cycles of regeneration. Some catalysts are extremely stable but are very slow. In addition, the catalyst has to be selective to the desired reaction pathway. For example, look at the following reaction. Conversion of N-paraffin to olefins with platinum catalyst supported on alumina. N-paraffin reacts reversibly to form olefins catalyzed by platinum supported on alumina. Alumina supported platinum catalyst is highly active but not selective to hydrogenation to form olefins. Various byproducts are formed in parallel and series reactions under the action of acid sites in alumina. In addition, rapid deactivation results caused by coke formation and fouling by carbonaceous material. How do you achieve the highly stable, selective and kinetically fast characteristics? That is by use of modifiers. The modifiers weaken the side reactions without affecting the desired reaction and also increases the stability. Depending on the nature of the process, the modifiers vary. For certain reactions involving platinum catalysts, metals such as arsenic, tin, germanium, lead and bismuth are used as modifiers. These metal elements not only enhance the selectivity of the reactions for desired products, but also improve the stability against fouling by heavy carbonaceous materials. In many catalytic reactions in refining and petrochemicals, the highly active catalyst element is dispersed into the catalyst support material having large surface area. Alumina is used as a support for many catalysts. It has excellent thermal stability and mechanical strength under processing, transport, and during regeneration, thus ensuring good stability. Shown in this table is the chemical composition of zeolite catalyst used in fluidized catalyst cracking of petroleum fractions in refineries. You can observe several metal elements in ppm level of concentration are used in the catalyst to improve the stability. This table shows some of the physical properties of FCC catalyst. Most important of them are the particle size and the surface area. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With the various related performance issues in catalytic processes, how do you select and design the reactor? What are the different types of catalytic reactors commonly used? What are their design basis? Do not miss the next video, Reactor Engineering. With this, we have come to the end of the presentation. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you have finished viewing the video. Share with your friends and colleagues to reach out to large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.